Our third and final kind of transformation is the kind where you stretch a graph and or compress it. Kind of like two sides of the same coin. Stretching and compressing our graphs. What does that look like? Well, first question, what does that look like? Do you remember what that function is? That's called the floor function, and it has the effect of rounding things down. Down, 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 down. So if I were to sort of make a pretend XY table, if you plug in x equals 0 into here, you round it down to 0. If you were to plug in x equal to 0.2, you would round it down to 0. If you were to plug in 0.4, you would round it down to 0. If you were to plug in 0.6, you would round it down to 0. If you were to plug in 0.8, you would round it down to 0. But if you plugged in 1, you would get 1. So that's what I call the first step. So I was plugging in all these x values. X is 0, 0.2, 0.4, 0.6, 0.8, and we were staying at y equals 0 until, open circle, you get to x equals 1, at which point you really do get y equals 1. So we've seen this before in lesson 56. This floor function basically gives you a set of steps. So I'm just going to, and once you've got the pattern, you can just trust and follow the pattern forever. So it's going in both directions. Doop-de-doo. We always got these solid dots on the left, open circles on the right. Make sure your open circles and solid dots are perfectly lined up like this, right? Perfectly lined up. Up, up, up. Okay. There's our floor function. And of course it does continue forever. I don't know if you want to keep, draw these things or what, but that's our floor function. So this, of course, is just a small part of the XY table, but I trust that you remember. It's a bunch of steps. Now, our key question for today, question 1 of 2 really, is what does that 2 going to do to us? 2f of x. Now, this is a transformation. This is saying take our function f of x, which in this case is this part, the floor function of x, and change it, multiply it by 2, and we will call the result g of x, give it a new name. So in other words, g of x is going to be 2 times the old function, like this. G of x is 2 times the floor function of x. What happens with, what does the 2 do? Well, you can kind of, maybe I'll just put that right over here. In fact, you can kind of do that right here. When you plug in 0, this rounds down to 0, and you multiply it by 2, it's still 0. And when you multiply in 0.2, when you plug in a 0.2, it rounds down to 0, and doubling it means it's still a 0, and that's going to be true all the time. And then when you finally plug in x equals 1, which rounds down to 1, you're then going to double it. And so it's going to go up to a 2. So we can see right away that the first thing that's going to change is we're going to have all this step is all going to be the same. It's always rounding down to 0. But then, boom! Instead of jumping up to just 1, we're jumping up to 2. And then it turns out that step's going to stay there as well. Now, what would happen if I plugged in 2 for x? Well, in the normal function, if you were round down to 2, you would get a 2. But with this function, you're rounding down the 2 to 2, but then you're doubling it. You get a 4, right? You round down the 2 to a 2, and then you times it by 2, you get a 4. So this point ends up here, right? We used to get a 2, now we got a 4. And then that step will stay the same, and so on. And by the way, it's going to work the same down here. This, instead of being down here at -1, it's going to be down here at -2, and this is going to be at -2, right? Wait a minute. I didn't want to draw it that way. I wanted to draw it this way. There we go. Instead of being at -1, it's going to be at -2. And then this, instead of being at -2, it's going to be at -4. This whole step is going to move down to -4, and so on. So it's still a set of steps. It's kind of climbing steeper, you might say. We call that a vertical stretch. Vertical stretch by a factor of 2. A vertical stretch by a factor of 2. So if you put a 2 in front, that's the thing that's doing it right there, right? So let's get this out of the way so it doesn't confuse us. Okay, cool. So if you put the 2 in front of the function, It's kind of like saying, you know, take what I used to get for outputs and double them. Keep multiplying them by 2. That's going to be a vertical stretch by a factor 2. Every y coordinate on the old graph, like even here, this used to have a y coordinate of 2. Well, that got doubled to a 4. Every y coordinate got doubled. This used to have a y coordinate of -3. Guess what? It's going to end up way down here at -6 someplace. Okay, so every y coordinate on the original blue graph gets doubled. That's what this 2 in front does. We call it a vertical stretch by a factor of 2. Take a quick look at something. What's the next page? Okay, cool. P.S. If you used a half in front, can you guess what the difference would be? Instead of having a 2 in front, we had a half in front. What would be the difference? Well, that would be called a vertical compression by a factor of 1/2. Because, again, you'd be taking all the old outputs that you used to get. We used to get, this was our old outputs. We're taking those, and instead of multiplying them by 2, if we multiply them by a half, they'll all get cut in half. You'd end up with something kind of skinnier down here. Or not skinnier, but less shallow, less steep, something like that. So, anyway, a 1/2 in front would be a vertical compression. A 2 in front is a vertical stretch. So the point is, put something in front, and you're going to do a vertical stretch or compress. If this is a 2, if this was a 3, that would be a vertical stretch by 3. If you put a 1/3 in front, it'd be a vertical compression by a 1/3, and so on. All the y coordinates would be 1/3 of what they used to be. Okay, so that's the whole idea of a stretch, a vertical stretch. Now I need to get a new color out because we're going to do the next one over here. Let's see. I guess we'll stick with the green. The 2 is in a different place, notice. Here, the 2 is in front. That was a vertical stretch. Make it a fraction, it's a compression. But that was a vertical stretch. Put a 2 in front, that's a vertical stretch. Now the 2 is inside. Go inside the function. Go inside the function, so to speak. Which means go here, inside. And change all x's to 2x's. Which is kind of what we mean when we say plug in 2x, right? You go where there's an x and you plug in a 2x. So change all the x's to 2x's. Okay, what would that look like here? That would look like, here's my function, absolute value of x, but I'm changing that to a 2x, like this. So it's a different move, for sure. And now I find myself wanting some space. Shrink. Here we go. I want to try to fit in a bit of an XY table here so we can see what that 2 inside is going to do. So again, if I plug in a 0, well, 2 times 0 is still 0, which rounds down to 0. Fine. Let me plug in a 0.2. Sure, why not? So 2 times 0.2 would make a 0.4, which rounds down to a 0. Fine. And let me actually put in a, I'm going to jump all the way to, well, no, let's put a 0.4 in. What else? We'll be safe. If I put a 0.4 in, 2 times 0.4 is going to be 0.8, which is still going to round down to 0. Okay, now I'm going to put in a 0.5. When I put in a 0.5, notice something's going to be different here. 2 times 0.5 is 1, and 1 rounds down to 1. What happened? Well, in the original function, when I plugged in x equals 1, that's when I jumped up to y equals 1. But in this function, I plug in a half, and I jump up to y equals 1. The step isn't as wide, in other words. So this new function, which I'm going to try to draw in green here, starts at the origin. It stays down here for a while like the old one did. But when x got to be a half, that's when y jumped up to 1. Now, it's going to be a nice step function. So if this step has a width of a half, you can kind of bet that all steps are going to have a width of a half. Try to make it look like solid circles on the left and open circles on the right. But that's what you've got. It's what would you call this? You would call this a compression in a horizontal kind of compression. Notice this blue step up here used to go from 1 to 2. Well, the 1 gets cut in half to a half, and the 2 gets cut in half to a 1. Instant replay. Let's do it on this one, this step here. This blue step, the original function, the step goes from x equals 2 to 3. Oh, look, I made an arrow. That's cool. It went from 2 to 3. Well, this x equals 2 gets cut in half to x equals 1. And this x equals 3 gets cut in half to 1.5. See what I mean? It's a horizontal compression by a factor of a half. Let's write this up here. So the 2, let's write it over here. This 2 does a horizontal compression, and that surprises people sometimes, by a factor of a half. Not a stretch, but it's actually a compression by a factor of a half. If you put a 2x there inside the function like that, you're going to actually end up squishing it in towards the y-axis. A horizontal compression squeezes, by the way, it squeezes both ends in towards the y-axis. So this point's going to get squished to here. This point, let's see, it's going to go like this, right? So this point goes to here, and then this point goes to here. Basically, you can just kind of keep the pattern going. It's going to look like this forever. Okay, so this is a horizontal compression. So again, horizontal compression by a factor of 1/2. Again, it's weird at first because you see a 2x and you expect something to get doubled, but it's actually the thing is being compressed horizontally. Okay, so this kind of goes back to, remember when we did this, when we did x plus 2, and you might have been expecting it to go to the right, but it went to the left. Yeah, when you go inside the function to make changes, it's kind of, you get counterintuitive effects. Maybe if you just remember that part, it'll help you keep this straight. So horizontal compression by a factor of half. By P.S., what if you wanted to stretch? Well, if you want to double it, if you want to stretch, you would put a fraction in there. Is a horizontal stretch by factor of 2. Okay. I think we should summarize this now. Let's come down to here. Summary. If you build a new function g of x by taking an old function f of x and multiplying it by 2, that will be a vertical stretch by a factor of 2. If instead you do half f of x, that'll be a vertical compression by a factor of 1/2. If you put the 2 in here like this, f of 2x, that's going to be a horizontal compression by a factor of 1/2. And if you wanted to do replace the x with the half x, that would be a horizontal stretch by a factor of 2. So we've got 4 kinds of stretch compressed combos going on here. Now the value, once you sort of internalize this, you gotta work with it, chomp on it, digest it a little. But once you've got it more or less almost memorized, or at least keep this handy, you can graph things more quickly because you know what to expect. Like square root of x. Remember what we expected with square root of x? Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. You expect this shape when you do the square root of x. Okay, well that's not what this is. This is 2 times the square root of x. It's vertically stretched by a factor of 2. So when y is 0, well, you double it, it's still 0. But when y is 1, it becomes 2. When x is 4, we used to have y is 2, but that gets doubled to a 4. It's twice as tall, in other words. It's times 2. It's twice as tall as the normal square root function. What's this thing? Well, again, square root of x, we have these basic points that we kind of have in the back of our head, 0, 0, 1, 1, 4, 2. But that's not what this is, because this is going to be a horizontal, but remember it's a compression. We expect a horizontal compression by a half. And so the point over here that's at x equals 4, it's going to occur at x equals 2. And this point that occurs at x equals 1 is going to occur at x equals a half. So let me kind of carefully try to erase these other things out of the way. Of course, being at x equals 0 is not going to change. So you end up with, it might look like it's being vertically stretched, but actually it's being horizontally compressed. I'll call this one vertical stretch by 2 right on the graph there. And it's a little bit of a difference. What's this? This would be square root of x function again. So again, 0, 0, 1, 1, 4, 2. There's your basic points. Except this time we have a vertical compression by a factor of a half, which means scrunch it down. Take this point, move it halfway down to the x-axis. Take this point, move it halfway down to the x-axis. You end up with this one. Let's get rid of that one. Okay, so it's been vertically compressed. And then here, you're going inside the function. You're multiplying x by a half. That's going to actually be a horizontal stretch by a factor of 2. So instead of going through 0, 0, 1, 1, 4, 2, horizontal stretch means, well, if x is 0, we don't change. But if x was 1, double it to 2. Here, x was 4, double it to 8. This thing's looking sort of like this. It's been horizontally stretched. And usually you don't want to. You want to keep all those things there. So you can sort of picture your graphs or even make your graphs much quicker if you have this expectation in your mind. I know what square root of x looks like, and putting the half there is just going to, you know, whatever, stretch it, compress it, which way, this horizontally, compressively, whatever. Okay, cool. So I think we have one more page. Let me double check. Yep, one more page. So kind of like in lesson 58, we did reflections in lesson 58, and then I said, well, what happens if you translate and reflect? Does it matter which order you do them in? And remember, sometimes it does, sometimes it doesn't, sometimes it does. Kind of want to revisit that theme here in blue. So we're going to take f of x equals absolute value of x. We're going to vertically stretch it by a factor of 2, and then we'll shift it down by 2. So first, let's just do that equation-wise speaking. We're starting with the absolute value of x. Vertical stretch by a factor of 2. What's that? That's when you take the function and double it. So take the absolute value function and double it. That's where you'll end up. Okay. Down by 2. How do you do that? That, you might remember, is where you take the function, whatever it looks like, and you subtract 2. So I got this 2 absolute value x, and I'm going to subtract 2. So that's what my function will look like. Now, what's the graph going to look like? Well, I'm going to just kind of go back to gray. I like going to gray here and saying, okay, first of all, you were saying that we started with the absolute value of x. Let's just kind of more or less bang that out there. Okay. And now let's do these two things. Let's first stretch it vertically. Double all your y coordinates. Here y is 0, doubles to 0. Here y is 1, doubles to 2. Here y is 2, doubles to 4. Same thing on the other side. So that's what it means to do a vertical stretch. Okay, that's the vertical stretch. Now go down. So I'll use blue to put my final graph in here. If I take that kind of a steeper looking pointy-ish absolute value and I move it down to 2, then that's going to end up there, that's going to end up there. Every single point is going down by 2. It's going to look something like this. And there's our final answer, something like that. I don't think I quite drew that right. It should, yeah, like that. That's better. That's a little better. Okay, so there. Now, if you wanted to prove to yourself that this equation was really giving you this graph, you could make a little XY table real quick, plug in things like, hey, if I plug in 0, what do I get? Well, 2 times 0 is 0, minus 2 is minus 2. Yes, we get that point, and so on. And I invite you to finish that XY table up. It'll work. Now, this next one, we're doing the same two transformations, a vertical stretch and a down, except here we're doing the down first and the vertical stretch second. So that's the only difference. Same two transformations, different order. First, let's look at the effect on the equations. So start with absolute value of x. Down by 2. Okay, your instructions for down by 2 are to take whatever your function is and subtract 2. My function is this. I'm going to subtract 2. Okay, that's that. Now, vertically stretch by a factor of 2. What's the instructions for that? You take whatever your function looks like and you double it. So now I'm going to take this function here and I'm going to double it. What does that look like? Be careful. It looks like this. Because if you double it, what you're saying is take my absolute value of x minus 2 and multiply it by 2. You have to distribute. So you get 2 absolute values of x minus 4. Okay, so notice again, this is not the same function. If you compare these two, they're not the same. So we did the same two kinds of maneuvers, but we did them in an opposite order. We're ending up with a different equation. That must mean we end up with a different graph. Let's see how the graph is different. So again, I'm going to start with my absolute value of x, which goes something like this. Okay, first I'm going to go down by 2. So that's going to end up something like this. Okay, so first I went down by 2. Now, get to blue, I'm going to take this thing and stretch it vertically by a factor of 2. You see this point at y equals 2? It goes to 4. You see this point at y equals 1? It goes to 2. You see this point at y equals 0? Well, if you double to 0, you're still at 0. You see this point at negative 1? Double it to negative 2. You see this point at negative 2? Double it to negative 4. Look at that action, huh? Over here, this point is at y equals negative 1. Double it to negative 2, and so on. So you get the same kind of thing, of course, on both sides. But if you compare what we had here to what we have here, you'll say, well, they look kind of similar, but they're not really in the same place. It's not really the same function in the end. So whether I went down or vertically stretched by a factor of 2, whichever one I did first, it ended up making a difference. So the summary here will be something to the effect of vertical actions being vertical stretch, vertical compression, up-down reflections, and by the way, reflections over the x-axis. Those are all vertical actions. That word is supposed to say actions. Vertical actions can interfere with each other, which means order matters. Horizontal actions. If you do a horizontal stretch or a horizontal compression or a left-right or reflect over the y-axis, right? These are all sort of horizontal actions, right? They can interfere with each other, i.e. order matters. What won't matter is if you were to say, take a point, first move it to the right, and then, I don't know, move it up. And that's, you know, if you moved it up first and then moved it to the right, it's not going to make a difference. If you mix horizontals and verticals, you know, one horizontal with one vertical is not going to be a problem.